Okay, so good evening, everyone, and welcome back to our periodic appointment with Rediscovering the Space, this cycle of inspirational speeches in the framework of the PhD program in Aerospace Science and Engineering here at Politecnico di Bari. In the past events, we have the opportunity to listen to very different presentations. So let's say visions from different angles of a common problem that is that of the aerospace. But today, to further underline the increasingly multidisciplinary nature of the research in the field, we are pleased to host Dr. Valentina Sumini, space architect and research affiliate at the MIT Media Lab. She will talk about space architecture. That is a fascinating topic on which also the Polytechnic of Bari has been involved for several years. So I really thank Valentina for being here today and for enriching our program. To all the participants, don't forget to interact with our speaker. So ask on the chat for our questions after the presentation. So now I will give the floor to Francesco Cupertino, Director of Politecnico di Bari, for a welcome greeting. Thank you, Francesco.
Thank you, Marco. I would like to welcome all of you, and in particular Valentina Sumini, and thanks her for her availability to be today with us. In the end, there is something good coming from the pandemic, the possibility of having very important speakers coming from all around the world with very different experiences. I will hope that we started this series of speeches completely online. Maybe before the end of this series of speech, we will have the opportunity to welcome to be in presence at Politecnico di Bari. We are doing our best so to let you find when you will be back at Politecnico. We are working so to let you find some renewed space, and the new Aula Magna is waiting for us. I hope that all the ongoing works will be finished by the end of the next summer. Hopefully, the next academic year will be something more similar to what we are used to have as academic years at universities. But by the way, we try to get the most from what we have. And today we are again together talking about aerospace. When we started the new PhD program in science and engineering for aerospace, we decided to put together two universities, University of Bari and Politecnico di Bari, because we were convinced that the multidisciplinary approach is the only approach that is compatible with the field of aerospace. It is a very important field, not only for science and for the development of all of our culture, I would say, for the future of human beings, because today we're starting talking about space architecture. Since I understand that being an engineering myself, I understand that architecture is the science related to the relationship between the human beings and the place where they live. When we talk about space architecture, we are assuming that there is a possibility that the human being will have the opportunity of living outside planet Earth, and this also means that we would have a second chance in case planet Earth would become no more good for humanity. And in this content, as Marco mentioned before, when we start the PhD program, we tried to take it as much multidisciplinary as possible, taking all the possible inspirational points, coming from our research laboratories, but also the opportunities coming from abroad. And this series of events, a series of speech, is aligned with the point of view I mentioned before. And today I'm particularly happy because bringing together science, engineering, and architecture is something that is strictly related with the idea beyond a polytechnic university, taking together in the same university industrial design, architecture, and engineering in something that as a contact point maybe in the space architecture. So it will be an opportunity of being together, engineers and architectures with something in common, the opportunity of sharing ideas, sharing a vision for one of our possible futures. So I give the floor to Annalinda Leglia. I thank also her for her availability of doing as a moderator this afternoon. She will introduce Valentina Sumini.
Thank you very much to the organizer of this lecture, and good afternoon to everybody. I'm delighted to introduce you Valentina Sumini. She is a postdoctoral researcher and space architect at MIT Media Lab in Responsive Environments and Space Exploration Initiative. And she is also a visiting professor at Politecnico di Milano, where she teaches architecture for human space exploration. Her background is very rich. She holds a PhD in preservation of architectural heritage and a bachelor in architecture and a master of science in architecture building engineering. So she put together different fields and experiences. And her work is aimed at developing design and architecture to sustain human life in extreme environments on Earth, but also at enabling human space exploration in low Earth orbit on the Moon and Mars. Her space architecture research focuses on democratized access to space by envisioning new computational design methods for multi-performance habitats, soft robotics prosthetics to enhance mobility in microgravity, and construction techniques using in situ resources. Over the years, she developed studies that she applies to different scenarios and award-winning competition projects, also organized by international agencies. Between the others, I'm just recalling some of them: a space hotel in low Earth orbit, a city on Mars for 10,000 inhabitants, which can be also ideally used on Earth, on our planet, in hostile areas such as deserts or icy areas, which is named Redwood Forest, and its generative design model. She also designed a system to extract ice and water from the subsurface of Mars and a moon village in collaboration with the architectural firm of Skidmore, Owings and Merrill and with the European Space Agency. Not least, she has been involved into the design of a soft robotic exoskeleton for enhancing movements and performance in microgravity. Her work has been presented in many places and journals, including, between the others, the Harvard Design Magazine, the Wall Street Journal, and Forbes. And she is also vice president of the Earth and Space Technical Committee of the American Society of Civil Engineers. Today, she will introduce us to her work on design and architectural solutions to support human life in extreme environments on Earth, and to enable human exploration of space in low Earth orbit on the Moon and Mars. So, Valentina, thank you for being here, and the floor is yours, and welcome again to the Polytechnic University of Bari. Thank you.
Thank you all for this invitation. I'm very happy and excited to be here with you. And thank you, Francesco, and thank you, Annalisa, for this extensive introduction. And I'm going to start my talk sharing my screen. Do you see the slide? Perfect.
Yes.
Okay, perfect. Yes, at the moment, I'm a researcher affiliate at MIT Media Lab. Has been today several years I'm involved in the space architecture research world, and being within the Responsive Environment Research Group and the Space Exploration Initiative, our main goal is designing for a multiplanetary future. And part of our research is really dedicated to define this vision and how, with our design skill set, can we really improve and enable humans to live in outer space and on other celestial bodies. Our research is focused on different fields within the Space Exploration Initiative and in the Media Lab, and what we are looking for are really like a solution that involves different disciplines together. So we are working on a multidisciplinary environment. This is actually the main concept of the MIT Media Lab itself, the antidisciplinarity of our projects. And the field relate to the use of robotics and artificial intelligence, inflatables and soft robotic structures, and all the world of additive manufacturing in zero-G, the augmented reality and virtual reality, how we can also bring art into space. So what you can see here is like a musical instrument that actually works, has been designed for microgravity experience, and also some work on spacesuits and all the wearable technology devices that will enhance and enable human space exploration in other environments. Specifically, my research is really focused on design across scale, from the human perspective up to the architectural infrastructural scale. As Annalisa mentioned before, I'm both architect and building engineer, and I'm really passionate about all the scales of the project with a real focus on human design factors that actually are involved and embedded in all the projects that I'm actually currently doing. And for developing this project, I usually works together with the entire world of robotics and computing. So developing computational design tool is also part of the game of being a space architect. If you really want to have a holistic approach to design that actually take into account different aspects and different objectives during the design phase, it's always important to define also new design tool that will help you designing your habitat, whatever is on low Earth orbit on the Moon or Mars. And what you can see here is my page at the Media Lab. As you can see, I work on a Moon Village project together with the European Space Agency and the Architectural Office at SOM. I work on Space Human. Space Human is an exoskeleton soft robotics that will help mobility and dexterity in microgravity. Tidmarsh Living Observatory Portal, it is a project that is dedicated to how we can really reconnect with nature in an artificial environment, but without using VR or augmented reality, but using the entire world of projection in order to actually create a sort of cocoon where to experience this connectedness with nature that I think is very important for a psychological aspect during a long-term exploration in space, but also as we experienced in our last year during COVID-19, when we were like isolated in our homes and we couldn't even go out. So the idea of having this sort of cocoon that helps you and surround with this sort of interface that reconnects you with nature, I think is one of the most interesting project for like human factor design principle. Orbiting is an art installation that we did with John Kubli, who is an artist, a German artist, and he wanted to actually dedicate this art piece to the idea of how we can really recreate the floating experience of microgravity. A Mars Boreal greenhouse, this is a project that has been done in collaboration between MIT and the Politecnico di Milano and Politecnico di Torino with the Alta Scuola Politecnica, and is an award-winning project with NASA. And I will talk about this project later on. And Persian Domes for Human Space Exploration on Mars is a project that's been developed together with the University of Houston in the Master in Space Architecture, and try to how we can really learn from ancient architecture like Persian domes to evolve it and optimize it for additive manufacturing on Mars. So today I would like just to introduce some of these projects, and with the idea to let you in this world of space architecture. One of the main thing you want to consider when designing for space is actually learning about existing architecture in that field. And last year we celebrated 20 years of activity on the International Space Station. It was an enormous project that's been deployed in 1999, and so 239 individuals and coming from 19 different countries, a beautiful international partnership and international collaboration that led to this beautiful piece of space architecture that is still active today. And one of the most beautiful parts of this project is, of course, the module cupola. That is the window that allows us to see the Earth from above. And this overview effect that actually is one of the most interesting experiences that astronauts perceive once they are on the ISS. And when trying to give a new contribution actually to the space architecture world, we had to understand very carefully where we are coming from. And we are coming from rigid and inflatable modules, actually. So we have an extensive knowledge on how we can really design this sort of aluminum can-shaped component, which the International Space Station is made of. And we had also an extensive research about all the inflatable structures that both NASA with the Trans Hub and Beagle Aerospace are developing for outer space. And the combination of the two actually creates a new possibility in how we can really define and experiment in this new type of architecture. What I think is interesting about inflatables, for example, inflatable solution that can be pressurized when they are like in situ, so when they are really in orbit or on the moon or Mars, is the idea that they can really be compacted and during the phase of launch, and then they can be deployed and pressurized while they're there. And with this concept, we designed the first project back in 2017. This wanted to be a space hotel designed using the existing module of the International Space Station and adding new modules for allowing space tourists to go there. What you can see here with this sort of flower of inflatable modules is the space hotel. They can host up to 6 tourists. And what we try to realize is inserting these hotel modules, for example, around the cupola module of the International Space Station, with the idea of allowing the tourists to see Earth from above and creating this awareness experience that I was talking to you before about this overview effect. And I think this one was one of the first projects that tried to combine together the knowledge of both rigid and inflatable element modules using the library of modules that was already available at the time in 2017. And but then we move forward. We try to understand which could be a solution, innovative solution for designing an infrastructure on the moon. And looking at the lunar environment, was something that we wanted to take into account, or the use, of course, of the in situ resources. And of course, there are like several um, interesting aspect in using, for example, the soil, the lunar regolith for 3D printing it and using actually to generate some sort of infrastructure components but also another interesting aspect is ice. And we wanted to locate actually the habitat in a place that is actually plenty of ice. In this case is the South Pole of the Moon. What you can see here are the two maps of the North Pole and the South Pole. And in the South Pole, we decided to locate the habitat and the Shackleton crater, mainly because in the shadow area of the Shackleton crater, we can find a source of ice that actually can be useful for sure if you want to enable humans to live in this environment. And actually another interesting feature of the Shackleton crater is like along the rim of the crater, we can have the peak of eternal light. Somehow we can really use some sort of sustainable energy sources like solar panels to have energy to sustain our infrastructure. And something that actually was interesting for us is understanding this type of constraints in terms, because we are used as architects and as to design for an environment here on Earth, specific environment and the specific constraints that we define every time we start a new project. And in this case, in the lunar environment, it's a very harsh and hostile environment because we don't have any sort of atmosphere and we are not protected against the cosmic radiation or micrometeorite impacts. And we have external thermal variation. We really need to look for a safe place where to land and actually build a safe infrastructure. And in order to achieve that goal, we tried to understand which could be the possibility that we had. So one possibility would have been designing and build all the modules here on Earth and then ship it to the moon. It could have been like, of course, composed by rigid modules as the International Space Station, as I showed you before. Could have been inflatable structure or a combination of the two, like a class 2 modular system. They have both combination of rigid elements and inflatable elements. Or could have been a class 3 in situ robotics. So we had like a combination of inflatable with a hybrid with regolith and other in situ material to integrate the habitat, a combination. And what we had to understand which one of these types of architecture worked the best for us. And to do that, I perform a multi-objective optimization, trying to understand on the Pareto front, which could have been a good solution to starting from, considering if you wanted to have rigid module or inflatable modules or using in situ resources. And we came out with the idea that using inflatable elements protected with the shield of lunar regolith would have been the best solution in terms of how we can really generate a bigger volume while minimizing the launch mass and maximizing the using of in situ resources. And this is a video of the project.
We choose to go down in this decade and do the other things. Not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept. One we are willing to postpone.
So here we are. We just landed on the Moon Village on the Moon. As I said before, this project was developed in partnership with SOM and ESA, and within MIT and ESA, we had 2 astronauts on board. At MIT side, we had Jeffrey Hoffman, and at ESA side, Claudine Herret. That is actually a French astronaut. And together with them, we came out with this solution that is very intriguing because we kind of generate a new shape in order to fulfill all the needs and requirements for this closed loop system deployed in each module. As you can see, this is a modular configuration, and the module will be built and shipped to the Moon and pressurized in there. And the combination of a rigid and inflatable structure allow us to do these volume extensions while we are there. We can really fold the inflatable membrane within the rocket payload fairing system, and we had this the rigid component that is this drill-based structure and this frame, and then using composite materials, and then we will sustain the habitat through different strategy. We have, for example, this habitation module will be connected to system of through an airlock system to different other modules, and with the food production and greenhouse system, we're going to have solar towers and power storage and in-situ resources shelter and production, sintered roads as infrastructure, and resource storage part, and of course we're going to have an extensive use of additive manufacturing in situ to perform all the shielding required using the lunar regolith and ice extraction for habitation purposes. To develop this project, the first thing we had to do is, of course, defining the mission goals, the objective of the first crew and the objective of the second crew, and dividing them with the type of activity they're going to perform every day, and within the habitat, and all the aspects related to the living, and all the extravehicular activity required, and of course all the operation that we had to plan in advance. And it's interesting because this has been possible only thanks to the astronauts that we had on board, because we are not really familiar with the everyday life activity of an astronaut, even if we are doing space architecture. And this is the first part to really understand, because the design, especially of the dimension of the module and the interiors, are driven by all this data and this very important and strategic information. And so one of the main interesting aspects about of course, all these activity they had to perform is understanding which are fixed in their everyday life and which one were flexible. And these two considerations led to a different design solution. Some interesting aspect was also related to all the aspect to the how we can maximize the volume and how and in which way we're going to allocate volume within the habitat, considering also how we can enhance behavioral health among the crew for a long-term mission. And of course, the configuration of different components of the habitat played a key role for the entire interior definition. Also the aspect to locate the activity that require more time than the others at the bottom of the habitat in order to be more protected against cosmic radiation is one of the main thinking aspect of the project. And to develop this sort of project within this highly multidisciplinary team, we perform several design thinking workshop altogether, try to solve for all these objectives. And another interesting aspect was related to the windows, because in terms of designing for human factors, it's important to design for being enabling the same overview effect that we have in the International Space Station through the Cupola module. So being able to look at outside to the lunar landscape in this case. And we chose the Shackleton crater mainly for the reason that I mentioned before. So the peak of eternal light along the rim of the crater, the possibility to find ice and other important in situ resources for maximizing in situ resource utilization, but also because from that site location, we are able to look at Earth, planet Earth. And this is one of the key elements that can drive a design and can also help astronauts to have a more happier, somehow, everyday life in their habitat. And windows, how you generate windows. The transparency in this sort of envelope strategy is always a difficult challenge to achieve, and we can use different stratigraphy, different material. We spread from aerogel to polyethylene to glass, and we define the solution within the rigid frame that we design. And so you can see from the plan, these elements consist in the rigid frame. What you can see here are the windows, while the rest, the trilobate petal shape, is made of inflatable membrane. Of course, also the lighting plays an important role for psychological effect. So it's important to generate a light that create a sort of a comfort zone within the astronauts. And this is also true in the greenhouse system, and where some lights that are good for plants are not necessarily good for humans. And so the idea of generating and find a spectrum of light that is good both for human and plants is also an important task to achieve. This is a view of the additive manufacturing technique we're going to use for 3D printing the lunar regolith around some portion of the module, because our goal is not 3D covering the entire module, but just the bottom portion of it to, as I say, because we are planning to locate the functions of the module that don't require lots of time for astronauts at the top of the module, while we want to protect at the most the bottom part of each module. This 3D printed lunar regolith allows to have this shielding against cosmic radiation and micrometeorite impact, and it will also cover the airlock of the infrastructure. While we designed a different type of solution, infrastructural solution for the modules that will require some manufacturing processes, both in situ utilization processes, and for them we design different modules also because they will require a different pressurization level. Because while we are trying to achieve habitation modules that can ideally go up to 1 atmosphere or 0.8 atmosphere, the other one can have less pressurized, and therefore can also can be optimized in terms of shape through different architectural solution. Is it true that when you design for this type of environment where you don't have an atmosphere outside, the main load condition is in the internal pressurization, and this is also drive the design, the material selection, and all these little details. For example, the connection between the membrane element with the rigid composite frame. Regarding the design of the interior, so we had a lot of anthropometric consideration. We had as manual, the NASA Human Integration Design Handbook that help us figuring out which could be like the different configuration of a human in reduced gravity, because on the moon we have 1/6 of gravity. And of course, the way we are gonna perceive the space, we're gonna behave within this space, is gonna be totally different. And I tried actually the lunar gravity through a parabolic flight where we tested different reduced gravity condition. I tried both the Martian one and the lunar one, and the lunar one is really intriguing because you can really jump extremely high without even realizing that you are jumping so high. And so the way we design the interiors are also driven by all these aspects related to mobility and of course ergonomics of space due to this reduced gravity. And this is a section of the habitat. As you can see, we have a metal composite column structure, we have this rigid frame, and we had some telescopic beams that are gonna deploy through hinge system once the membrane, the inflatable membrane will be pressurized. And we have structural windows in this rigid frame, and we couldn't insert windows in the membrane because, as I mentioned before, the membrane is going to be folded within the payload fairing system, and we also have this sort of hole at the middle, like a shaft. In the middle of this component, and with a sort of access ladder that allows you to easily go up and down to different levels of the habitat. What you can see here at the right, those are the volumetric dimension that we use to, there's a volume by zoning for all the habitat functions. And here, a rendering of the interiors. As you can see here, when you design for a space architecture environment, you really have a little volume. And so you are compressed in a small habitable space. And what is interesting in here is like how we can really achieve a high level of privacy within this shared volume. And it's not easy at all. So this module has been designed to host for astronauts, and for all of them, we defined a sort of a small private room. Up to now, the International Space Station, they don't have so much space. They are like really confined in little elements that have a sort of sleeping bag. But what we wanted to recreate here is a sort of really a cocoon, a space where they can have their own privacy and reconnect with home, with Earth. And so this is why we inserted a screen. We are planning to use augmented reality. We made the space for having a personal plant inside, and also bring, we put some books. Hopefully we can bring some books with us, but the main, and holograms to, of course, generate some sort of different visual elements within the habitat. And I think it's very interesting, this part, and this was part of the interiors was designed together with astronauts, that they suffer somehow the lack of privacy, the lack of private space within the space, a space architecture system. And also about flight system. So as I said before, our project has to be deployed while in there, but it's going to be almost entirely built on Earth and then transferred within thanks to a rocket system up to the moon. And so we had to take into account all the dimension, the dynamic volume of the payload fairing system that we had that are available right now. And our project could be inserted inside the Falcon Heavy and the New Glenn. And so considering these two aspects, we made a nice rendering of how it's going to look like. The picture in the center, you see, of course, the module that has been folded to fit within the rocket payload fairing system, and the other one once it's pressurized. So you can see the difference, the volumetric difference between the two configurations of the modules. And then Mars. Related to Mars, the project that I wanted to mention to you today is the project of how we're going to generate food on Mars. So it's a greenhouse project that we developed together with Alta Scuola Politecnica for this award-winning NASA challenge. And it's an intriguing project because actually incorporate the knowledge that NASA did in the past year with the Ice Dome project, the idea of having a habitat for astronauts that are going to live on Mars for 600 days. Because of course, for orbital mechanics, the travel is longer. We have to spend more time on the planet than like in case of the moon. And so we are designing one for Mars for 600 days of permanence according to this competition. And the project is, as I say, takes advantage of a previous NASA knowledge of the Mars-sized dome that you can see here on the left, where you have all the housing part and the lab house, the laboratory housing for the astronauts. And then we had to design a greenhouse system that's going to sustain, in terms of nutrients, 100% the astronauts. And made a calculation for an astronaut per day. We are considering 3,000 kilocalories. So our greenhouse system is based on hydroponic system, just to allow to grow enough plants to sustain all these 4 astronauts for 600 days. The project take advantage of the reduced gravity that we're going to find on Mars. The idea is having a germination area at the bottom, and when the plants are ready, they're going to be lifted up to the top of the spiral, and the trays will be placed at the top, and they're going to flow down thanks to reduced gravity while they grow. And so you will always have a new cycle of plants coming out for this system. And even in this case, we are considering the concept of operation requiring autonomous deployment. And after the launch, the greenhouse will take 6 months to arrive on Mars, and then we autonomously deploy, meaning that you're going to have the pressurization, of course, will take place. We're going to have the deployment of the membrane, all the telescopic elements like the column and the beam are going to take place, and the spiral that is compacted during the launch will actually be deployed as well. And then we're going to have an extensive work to do for extracting ice from the surface of Mars, because as I said before, this project arose from this knowledge for the Mars-sized dome, and I wanted to have the same sort of strategy. So we wanted to have this double layer membrane that has been insulated through a gas layer for thermal insulation, but also the cosmic radiation protection has, in this case, done through ice. And to extract the ice and fill all the volume required for generating this sort of shielding against cosmic radiation requires almost 2 years. So the greenhouse system needs to be deployed 2 years before astronauts' arrival. And what I want to show here is a video of the project. So as you have probably noticed, there are like many portions of the habitat that actually are dedicated to the reconnectedness with nature. So we wanted to develop this project of a greenhouse, not only considering the food aspect, the food production aspect. We wanted to generate a space where human and astronauts in this long-term mission could really dedicate and spend some time in dealing with plants. And this is absolutely important for a long-term mission because we're going to miss nature, we're going to miss planet Earth, and regenerating this connection with nature is one of the most important aspects. One of the interesting elements that we consider, for example, is the water reservoir that we inserted at the top of the habitat. And this water reservoir helps the hydroponics, actually is also placed at the top to allow to hydrate the hydroponic system and activate the hydroponic greenhouse system along the spiral. And we decided to generate a sort of waterfall with the tiny little drops, like a sort of rainy waterfall, just to recreate the sound of rain, the sound of water falling down that we have here on Earth, just for mental wellness. And as I say, when designing for long-term mission, this aspect is very important. So we try to generate solutions that also take into account this extremely important component. And the last project I want to present to you is a little bit provocative. It's a project that we designed together with a designer from La Sapienza who was visiting MIT Media Lab a few years ago, as Manuel Muccillo, and together with him came out with this idea of how we're gonna augment human in a reduced environment, such as, for example, low Earth orbit, with this idea of democratizing the access to space, not only to astronauts who have a serious training to have and live this experience. We wanted to open up to also space tourists. And the idea, the floating experience beyond the microgravity environment is really fascinating and have some similarity with the, for example, swimming. And we look at the undersea world with lots of interest because, for example, the similarity of the seahorses and the way, for example, they use their tail to navigate the underwater ecosystem, to grab, to handles, for example, like in this picture you can see, and also to grasp objects. And because of this three ability that the seahorse tail has, we decided to frame the project within this sort of a biomimetic design. And we designed a tail, a space tail for astronauts or for humans who want to go into space. And we took advantage of the space, some space research has been developed also together with NASA about a body restraint tether. The body restraint tether is an element that helps astronauts to be safe during extravehicular activity when they are outside the International Space Station, for example, and they really need to, for example, grasp the handles in order to secure their stability and why they are doing this operation. And so we decided to improve somehow this concept and transform it into an autonomous soft robotic tail that would enhance human performances in this microgravity environment. Using, as I say, soft robotics, that in our case translating using 36 air chambers that were autonomously inflating and deflating in order to achieve different configuration, different curvature, and enabling, for example, the possibility to grasp into handles and objects and being able to reorient the body posture while in microgravity. A key element was absolutely important for the project was also having a containing sleeve that was sensorized. So we used this smart textile system to understand, of course, the behavior of the tail in microgravity, and also to have data after the parabolic flight that we performed. And this is a picture of the team who flew with me. We had also Katie Coleman, who is an astronaut in here. And what you can see here is the team of the Space Exploration Initiative and Professor Joseph Paradiso I'm working with. And what was really fascinating about this experience was the possibility really to understand how astronauts feel on the International Space Station, not having any more a hierarchy of space, not having any more a ceiling or a floor or walls, but having all a surrounding environment that has no hierarchy and can be really a total floating experience like underwater environment. And what you can see here is the result of the project. This for example, I wanted to show during this parabola that each parabola lasts 30 seconds. So you have a very short time frame to really perform in microgravity, and we had a series of 20 parabolas, so we performed 20 times this reduced gravity condition. And what was fascinating, this weightless experience allowed me to understand how the tail works and how really activating the air chamber were changing the orientation of my body posture. We're gonna fly again in a few months, and we are adding on top of that an object tracking camera that will be able to track and define the targets, okay, and try to grasp it through, of course, different tail configuration. But this project actually is just the beginning of a more in-depth study on how we can really improve humans' life in space. And this is a recent article I just finished publishing with the Professor Domenico Pratechiz at the University of Siena and the Istituto Italiano di Tecnologia about telehealth and big data for human space flight. And so we really try to understand how we can really help them through telehealth system using, of course, some of the technology, enabling technology that we are developing at these research institutes to really improve their quality of life and of course, advance their responsiveness once something bad could happen, for example. And telehealth is kind of the future in terms of also the association with big data, artificial intelligence, to really solve for these problems. And I think the world of human-computer interaction, this is just a beginning of a bigger story. And I say that also to introduce the workshop I'm organizing for CHI. CHI is a conference of human-computer interaction, where we are going to collect very interesting studies about how we're going to really reuse even some of the design solutions that we thought for Earth, but in extreme environment like space, how they are going to evolve. And it's interesting because we received more than 50 papers among authors that are across from all different parts of the world. It was a very fascinating experiment, and And we received several papers on how we can recreate a responsive environment within a habitat in terms of wearable technology, and how we're going to apply IoT in different fields, how we're going to reconfigure habitats in space, how we're going to augment humans in so many different ways. It can be really augmented reality, but can be much more than that. And we can use a smart textile or other type of smart device to monitor their health and help them to training for before an extravehicular activity and so on. And so I'm very excited, and I think this is gonna a new discipline that's gonna rise up in the next years, and we're gonna see very exciting projects. I'm also very excited about it, and I'm happy to contribute to these huge research opportunities. And I'm very thankful for having that possibility. And last but not the least, I wanted to talk a little bit about the successful experience that I had at Politecnico di Milano during my visiting professorship position this year, teaching the first course open to both bachelor and master students in architecture and construction in architecture for human space exploration. I'm also very pleased to inform you that your Politecnico di Bari PhD student Vittorio Netti was my teaching assistant, and we enjoyed a lot teaching, and I was also reviewing all these exciting projects. We had almost 20 projects that have been developed in such a short time frame of a semester. And I wanted to show like a brief overview of some of the final posters that we had. For example, we had this project Infold that use and inflatable technology together with origami structure to define habitats on the lunar surface within this modular system, and different solutions how we could aggregate and populate an entire ecosystem using the same inflatable origami structure. We had a Dissolution for Mars instead, how we're going to populate a crater on Mars reusing the landing module and build around it using in situ resources, an entire ecosystem, including also greenhouse and plants. So this was really a fascinating project, considering also the closed loop system and reusing everything, so not waste at all during the mission. For Mars. And this project, Mars Ba, was also really fascinating, and took inspiration by the work done by Search Plus and using 3D printed ice for designing houses for Mars, and developed it further, thinking how many layers we could have, a different environment with different pressurization levels, and how we are going to define this habitation model surrounded by, again, a greenhouse system that uses hydroponics around the ice. They're going to be 3D printed. And they're considering this within, again, a modular system. And then the ice drop, it is actually also an intriguing project, because they, instead of defining one unique solution for the envelope, they decided to differentiate the envelope according to the different functions within this habitat ecosystem. And so we had a more translucent element. They use, for example, water and polyethylene as a shielding element and strategy, sorry. And also we have some regolith domes devoted to the areas where astronauts will spend most of their time. And just to say that, I'm very thankful for this opportunity, and you can follow us. We are slowly publishing the project on our Instagram page, and you're welcome to follow us. And thank you again for this opportunity. It was a pleasure giving this talk to you. I hope you like it. Thank you.
So thank you very much for this really inspiring lecture and presentation of your work. It was particularly interesting for me. I mean, I'm an architect, so maybe I'm one of the not engineers here, but I also teach landscape architecture. And I think that this is a very important point in connection on your work. I mean, I have tons of questions. I will just ask you 2 or 3, and then I will leave the floor for to the others. But the first one is really related to this role that something which seems to be very far from space architecture can have in the design of new habitats on the moon or Mars and so on. Following your listening your presentation, you talk about Persian domes as references for this additive manufacturing. Looking at the settlement on the moon, I saw these houses inside these craters, no, on the moon. And those are some typical way of settling that people on Earth use in very hard environment to settle down and to find a better environment, no? So it seems to me that this is something maybe also related to your background, that you know, preservation of Earth, and then I want to joke, to make a joke with something that our rector said, no? That maybe when we will destroy our planet, we will go to other places. We will find other places where to live, but maybe landscape can and sustainable in a way architecture can show us a way, no? How to design on our planet or on moon or on Mars, following some really sustainable idea of settlements and design. And this is one point. The other point, and then I will stop talking about gardens and landscape as well, is related to the interior design of the houses and of these greenhouses. I found very interesting the way how you moved from considering vegetation as something which is also is just needed, no, for food and for something which is needed for the human life, to something which can heal, no? On our planet there is this idea of designing healing gardens to cure in a way, no, our souls, no, to better allow us to live. And this is something related to hospitals, to something but in the space, this can become something very keen for living outside our planet. So I found very interesting this connection, no, between a nature which is not there, but that we can recreate in a way in our environment, no? So, and I don't know if this is a question or some comments, but I would like to have some feedback from your side about this. Thank you.
Yes, thank you, Annalinda, for your question. That I really thank you, because there these are 2 questions I really love to talk about. The sustainability is one of the key elements of all these projects, actually, and what I usually teach to my students is really this. So when we design a closed-loop system for the moon or Mars or for outer space somehow, like a space architecture solution, we are really focused on a design in terms of minimizing the use of resources. So we are sustainable since the beginning, because we have so many issues, like we can't bring lots of mass from Earth, and we want to minimize the impact that we're going to have on the lunar and Martian environment while we are in there. And so it will not be feasible not to be respectful of this new environment. And of course, as you mentioned, mentioned, my PhD architecture heritage really helps in this case because, yeah, I'm not like an explorer and I don't want to use all the resources to build, but I'm really more focused on how we can do using a strategic governance of the resources and using consultation. And I think this would have been like a global effort doing that we should do in partnership with different space agency companies and all the actors involved, try to concertate in a way the governance of the in situ resources, where to strategically plan an infrastructure or a village or maybe one day even a city, as was the plan for the Mars City Design Project. And so this is something that I'm really interested in, and I think, you know, my project, I'm really focused on how we can really minimize the use of materials and how we're going to also reuse waste. So, for example, in the project of the greenhouse, we are exchanging resources from the Mars zone to the greenhouse in a very smart way, in order to really not have any sort of peak of energy consumption, in order to have a distributed, for example, the energy requirements that we're going to have in there. And we were also considering all the waste that we're going to have from the plants and how we're going to reuse them. And so, for example, in the International Space Station at the moment, they are really keen on how we're going to reuse materials and resources. They're recycling the urine, for example, and it becomes again water. And this is just a short example of how we can reuse something, but there are like a lot of solution to be explored within this waste strategy, and reconfigure some material and in other objects. And so now, for example, I'm also interested in space food design, and how we are going to really design a space menu for these astronauts on Mars, and how we're going to reuse the waste for that to generating, for example, other type of materials and elements. And there's also a lot of study, for example, also the Istituto Italiano di Tecnologia, where they're using, for example, tomato to making materials like plates or whatever. And so you can really think of everything, and how this is a global, like a very 360-degree effort. And solving for this means solving for all the United Nations Sustainable Development Goals by 2030. And so this is the great lesson that we have to learn and apply here on Earth ASAP immediately, if you want to really save our beautiful planet. Because I don't believe there are going to be planet B. I think we will have to learn from this experience and how it's designed to better improve life here on Earth, and is our mission as humankind, and we really need to devote our life for that. And every time we learn and we design something for space, we are actually getting two lessons. Lesson learned to design better again for a new version of space, but we are also learning for how better design here on Earth. And to reply to your second question about interior design, greenhouses and vegetation to heal, I totally, of course, I'm totally agree with you. The healing properties of reconnectedness with nature are incredibly powerful. And we had an experience, I think all of us this year during the pandemic, when we were like obliged to stay in our houses. And I think the first day we had the opportunity to really go out, I went to a park, and most of the people I know did the same. And this is just a small example. And now most of my small apartment is also full of plants. And this for me is like an example of how we really need nature. Because while during a human space flight mission, we are really outside our comfort zone. And so, we kind of have, our body kind of have an allergic reaction to the outer space. We are in an environment that is not our environment. We are not meant to, we are not designed to survive in a reduced gravity and exposed to radiation or all these environmental hazards. We are designed to live here on planet Earth. So every time we go out, we are really out of our comfort zone and our ecosystem, and we need all this infrastructure to protect our body, protect ourselves in order to survive. But if for a long-term mission of years, like the one on Mars, surviving is not enough. because we are going to compromise our mental health and our behavioral health among like the crew members. And so this is why it's so important, as you mentioned, reconnect to nature, both in a physical way, if through the wind, for example, a greenhouse project. And for example, one key element of the greenhouse that I didn't mention, that along the spiral of the plants, there's an outer spiral just for astronauts. And this to allow astronauts to have a walk in the greenhouse. And so we are not really just minimizing the material, maximizing, of course, the production, but we wanted to also have a space dedicated to this reconnection with nature that is so important. So thank you for asking. Actually, I really love your question.
Thank you. And now I want to leave the floor to the other people who are here, who are willing to ask you something. The first question is by Professor Vito Albino, who is here and I think ready to...
Yeah.
Okay.
Okay.
I don't see you. Okay. No, okay.
Thank you so much. It's a very inspiring speech, and I'm really happy to hear you at Polytechnic of Bari. So basically, I wish to say that I'm not an architect, I am an engineer, but I want to ask you a couple of questions related to different topics, sociology and legal aspects. About sociology, I wish to ask you if you are including in your perspective sociological issues, because people have to live, especially when you talk about Mars. People have to live a long time in those houses, and then they have to interact each other, and then some problems can rise because, of course, we are sociological animals, so we need to interact with each other. And the second question is related to legal aspects, and in this case, I don't know if you are considering also in your design perspective the topic of ownership or the topic of real estate. Of course, this can be a problem that can rise in the next future, but of course, when we talk about house, the topic of legal aspects can be important. Thank you.
Yeah, so regarding the sociological issue, I think, yes, so there's a part of the research that we are currently doing, the Space Exploration Initiative, in which actually I'm not, so there are like several aspects related to how we're going to improve sociology and try to design an environment that can also lead to conflict, if a conflict arises, a conflict resolution, right? So how we're going to design our interiors to be responsive to that. And this actually technology might help. So there are a lot of study on how we can use robots that can actually help us in terms of really calming down and trying to kind of create sort of empathy with us. And there are like an extensive research in social robots in that. And some of them, I think, I show one slide at the beginning with these robots in this during a parabolic flight. And this one has been built and just to do that, actually. And how we're going to reconnect also with using sort of IoT strategy to help astronauts in their behavioral health. And regarding to the sociological aspect, also I'm very fascinated about the way also design and interiors can really help. And this is the reason why in one of the lectures during my course at Politecnico di Milano, I invited a psychologist just also to inform students that there's this aspect that is actually very important, because on Earth, we are living in our comfort zone, as I said before. So we are really in our environment, and it's easy to say, okay, I'm going out, having a walk and relax, but you can't do the same. So if you want to have a walk, you need to go next to a extracurricular activity, and to plan that you need hours of dedication, and some other astronauts are gonna need to help you. So it's really like a totally different experience. And this is the reason why it's so important having an astronaut training. So we are devoting our research with the idea of democratizing the access to space to everyone. But I think it's also important to say that when an astronaut goes, is also because has previously done a series of training really related in analog structure and learning how to behave and having a successful mission with having the entire a cohesion among the crew members. And so I think this is the reason why we should send first astronaut, because they have the knowledge and experience to handle that situation and having a proper conflict resolution strategy in case conflicts arise. And if you read some books related to some astronaut flights, like for example, Paolo Nespoli, he made a beautiful story about his experience and what happened during his mission he spent on the ISS. I think he spent up to 9 months over there. So many things can happen in 9 months. And so he made this excursion like which strategies apply actually to solve that situation. And so important, actually, it's really so important. And so regarding the legal aspect, so what all our projects actually, to be honest with you, we are really focused on the research and the technical aspect. And when I mentioned the problem of the governance and the partnership, public-private partnership, I mentioned that because I think it's important and we should replicate the same model of the International Space Agency. However, reading at the news, we don't see that. So we see this sort of space race led, of course, by few millionaires and some agreements among different space agencies. And I think this and that is a little bit complicated to even foresee how it's going to evolve the situation in the future, because as I say, that the governance of the limited in situ resources that we have is so important, and we need to be extremely strategic in that. And so we really need to have all the actors on the same table, and we need to explore as a humanity, not as countries or with national interests or private interests. So thank you again for your question. I think that Antarctic can be an inspiration for us as well as the International Space Station.
Thank you very much.
So thank you again. Now we have a question from Marcello Spagnolo, who is here. Maybe. I don't see him. I don't know if he's ready or not.
Hello?
Yes, okay.
Okay, good evening. Thanks for the interesting lecture. I also wrote the question, but I give the voice there now. So my question was related to the fact of the space architecture, not only for in situ infrastructure like human settlement in Moon or Mars, but also inside spaceships, because reaching Mars is a long duration flight, 3 to 4 months. So in your interesting studies, did you ever analyze also which kind of space architecture you can envisage for spaceship, which has to carry humans for 3-4 days flight or 3-4 months flight to Mars? Thanks.
Yes, actually, this is for sure a project that I would like to do. And at the moment, I didn't have the chance to do this sort of project, partially because we focus on every year challenges, competition that we participate with the students through NASA or other organization. But so I didn't have the chance yet to do this sort of study, but I think, as you mentioned, it's really important also to consider the flight. And yes, this is something that I would really like to do in the future. And there are so many lessons to learn from the actual study on the International Space Station and how this could evolve into a spaceship that could actually reach other planets. But this is something that I would really be interested in developing in the future, definitely.
Okay, thank you. Thank you.
So now we have Giuseppe de Villanova with another question.
You can hear me?
Yes.
Okay. Okay. Good evening, everyone, and thanks for the very interesting lecture. And I have seen in your beautiful building you have let us see that they are very like cactus, some of them, and so there is very much nature in this style. And so I want to know if it is correct. How much have you get inspired by nature, and if this inspiration is get also to the inner side of the structures, and how these buildings are anchored to the soil. And since for me, I like very much 3D printing. Indeed, I think that the man, when I leave the caves, has become to start printing. Okay, printing buildings actually. And so I want to know what are the devices used to avoid the problems related to the 3D printing in microgravity setting. That's all.
Okay, thank you. Yeah, so I mean, I probably didn't show the project today, but probably the project you read about is the Mars City Design project that actually resembles a gigantic tree structure. So this project, for example, came out with this sort of biomimetic design of a forest. It is named Redwood Forest, and the idea was in that sense try to colonize somehow the space of a crater in order to be able to generate a series of habitable volumes that could be both above ground and below ground. The idea in there was, that for example, on the surface of Mars, you don't really have water because it sublimates, right? Because of the condition, you don't have atmosphere and so on. So the idea was to extract the ice that is present below ground with the subsurface of Mars. And so drilling down and extract the ice and use the ice to vehiculate around these shells, this element, these dome-like shells, to protect the inhabitants in there against cosmic radiation, because through 1.5 meters, 2 meters of ice, you can really generate this protection. And the idea in there was having this flow of water within the habitat. Okay, and the habitat has this dome-like shape that inside has a series of branches. The branches have been optimized using force density method in order to have only tensile stress. And so the idea in there was just because you have this internal pressurization load condition, everything it works in tension. And so the idea was really optimizing this configuration, and it came out as a branch structure because I really wanted to kind of mimic the way trees on Earth vehiculate water from the roots up to the leaves. And so the idea of generating this branch structure came out from this analogy, but has been optimized for the Martian environment in that sense. And of course, the load condition of the ice was not enough to counteract internal pressurization load, that therefore remains the main load condition. What was fascinating in the project, the stratigraphy material that led to have a serious protection against cosmic radiation was composed by polyethylene, and it was like 25 centimeters of polyethylene, 1.5 meter of water, and another 25 meter of lead glass. And all these elements, there are studies from NASA that prove that it's possible to create and generate these materials in situ using in situ resources, starting from the Martian regolith. However, the idea was not 3D printing in that project, but was mainly really generate some sort of tessellation of this material and combine it into through a frame structure. The frame structure could have been potentially 3D printing using regolith. Regarding 3D printing in microgravity, so 3D printing in microgravity is something that I personally didn't explore, and I don't believe is going to work in microgravity condition. We might think that we can use 3D printing for sure in reduced gravities on the moon and Mars, but I personally think that in microgravity is really too difficult to work it out. And we had some experiment on a parabolic flight using, for example, a glue gun. And during the flight, it was almost impossible to drive the flow of materials, and because of the absence of gravity. So, given this experiment, I'm not really confident, but maybe I'm wrong. But sure, there's a lot of possibility to improve it. Let's say that. But at the moment, I don't see it as a feasible option. I will focus more on 3D printing and reduce gravity environment like the moon and Mars. And I know that you have Professor Falacara and who is working on that. So I think you're going in the right direction in reduce environment, reduce the gravity environment and not in microgravity. But perhaps also using some different type of additives, some uses magnets. It's possible to kind of attract the materials microgravity as well. But I mean, it requires an extensive research to improve. At the moment, we are not there yet.
Okay, thanks. And since I am sure that Marco will invite you to be in Italy, I want to suggest you to see some photos of a little town in Puglia. It is called Alberobello, and it is peculiar since it is it is modular. So in every family, when there was born a son, they build another of this building. So the picture, the structure, the modular structure of your plants, in some sense, are very similar to this one. And it's a very nice place, and I hope you will be able to see it. Okay.
Yeah, I mean, thank you for the invitation. And if Marco organize,
sure, Marco will surely organize it. Okay, for you. Thanks a lot again for all the answers. Okay.
Yeah.
So now we have another question by Lorenzo Santoro.
Thank you. Can you hear me?
Yes.
Good evening. I am a PhD student in mechanical engineering at the Polytechnic of Bari. I would like to ask if the arrangement of the housing modules on the lunar or Mars ground is inspired by typical housing configuration of insects or animals such as bees, ants. That is, are there any natural living patterns or framework that can provide inspiration for human life on the moon, Mars, or space in general? Thank you.
Oh, yes. I mean, lots of my students are, for example, focusing on beehive systems because the possibility to maximize the interfaces. And there are some research that I think are interesting on how we can be inspired by how ants collaborate together, or like termites are built. And so there are a lot of research in biomimicry and for both architecture, and not many actually apply to space architecture. I think there's a potential in there to explore something new, but I think at the moment I only see several big high structure in most of the project that I see, both with what we apply and also in our students. And I think probably we could explore a different type of interconnectedness, for example, derived more a spatial connection, because now we are focusing, for example, on two-dimensional connections element, but probably in the future, especially if we want to design within the lava tubes, for example, we can explore different configuration and try to connect in a different ways. And so if you're interested in that topic, I would suggest you to explore it, because you might end up having interesting results, for sure.
Thank you very much.
I turn on the light, I'm sorry.
We were supposed to, yeah, okay, to finish earlier. But there are some other few questions. One is from Francesco Cafaro, who is here. Francesco? I don't know if he's not ready. Maybe Marco, do you want to go first? And then we will give the floor to Francesco.
Yes, Analinda, thanks. I have two curiosities. I cannot say they are really questions. The first one is maybe there was the details in the presentation, I missed it. How long does it take to build the entire structure like the greenhouse on Mars? How many times?
Well, yeah, so the greenhouse will be autonomously deployed on Mars. Therefore, it means that it's going to be sent over there already integrated. It's going to be pre-integrated, sent to Mars, deployed on Mars. What we are going to do in Mars is integrated with the ice to generate and the gas layer actually to generate the thermal insulation and the protection against cosmic radiation. But and then this will take 2 years. But only the integration with the Martian ice. But it's going to be sent there fully already pre-integrated and assembled.
Okay, thank you.
So I don't have the data. If you want to build it from scratch over there, I mean, it's going to take a long time, because if it's only the shielding, it's going to take 2 years. You can imagine also defining all the materials, and then you need also power source to generate all of that infrastructure.
Sure, thank you. And the second curiosity is that in your idea of human life on another planet such as Mars, is there space for entertainment? So how to combine an harsh environment with the need for being outside that humans have? So maybe this question is related to the isolation of this particular period. So do you have any smart and brilliant solutions for common spaces like transparent domes or something like that, in order to be outside without living in the harsh environment? Thanks.
Yes, definitely. The translucency of the envelope, I think, is one of the key elements to actually see the Marscape is so important. And so part of the project, like the one defined with ice and the water, really are looking to that in that aspect, because entertainment is important. But in case we are also considering how it's going to look like the habitat if you don't have any windows, for example. If you design inside for example, a lava tube on Mars. And there are some researchers that are going to use, for example, projections on that and holograms to try to recreate a nice environment. And in that direction, I actually suggest a nice paper published on Acta Astronautica by Olga Banova in 2018, who is really focusing on the projections and as artificial windows for the outside. So what you can do when you cannot really go and see outside.
Thank you.
Now I see
I'm
on
ready.
screen Francesco Caffaro. Yes,
Francesco
okay.
Caffaro.
Please.
Okay, good evening. First of all, thank you very much for your nice lecture. And if I understand correctly, the water reservoir for your main building of the habitat on Mars is in your design on the top of the building. Is it correct?
No, sorry, could you please?
The water reservoir
Yeah.
in your design for the main building of the habitat on Mars is on the top of the building. Is it correct?
Yeah.
Okay. So my question is, did you assess in some way inertial effects on this water mass of Mars quakes in terms of bending moments, for example, on the building?
Yes, we actually did a finite element model of the entire habitat to assess and prove that. And because we have ice overall for the shielding, okay, but then we also had this concentrated mass of water that is considered at the top. And actually, given the fact that the weight of that of the entire mass with the reduced gravity of 1/3 is not again enough to counteract the internal pressurization that remains the main load. So we actually didn't notice any important effect to that. Plus, it's a really symmetric structure, and so it really behaves very well with the overall geometry and the topology optimization that we did of the envelope to that. We didn't want to generate the same sort of a dome configuration, but actually I want to show you something. For example, let me see if I found the other picture of another solution. I just need to, I want to show you. I'm not sure if I, yeah, so I want to show you, give me a few seconds.
Yes, no problem.
I don't know if you are, do you see this? The redwood forest?
Yeah, yes, I can see.
Yeah, for example, this project instead, the water was not located at the top. For example, we choose to create this cistern at the bottom. So because we were extracting the ice and keep it down and then veiculate along the branches and the outer shell. And all the configuration that we had for that instead was really optimizing the branch structure while performing, of course, this analysis of the root system, calculating the amount of water required to cover the branch, and automatically was recalculating branch, optimizing,
Okay.
optimizing for this using again a force density method, and then we optimize with the idea of generating a frame for the tessellation that I mentioned before to cover it with this polyethylene water and lead glass stratigraphy. Try to how we're going to recreate the sequence of structure without generating any support, like the Brunelleschi dome in Florence. So without any sort of construction support system. And the other one was really the effect of the gravity was not really visible. And but what we did, thanks to the University of Bologna, was a Monte Carlo simulation related to the neutron dose at different levels of the habitat. And this was very intriguing because we understood, for example, how the neutron dose varies according to the shape and the topology of the surfaces, and how the branch structure was useful to protect a certain area of the architectural space instead of other areas. And this would lead us to redefine the interiors driven by this data, actually. So the blue areas are the one, the safest one for us, but the red ones are the ones that actually are more exposed. The stratigraphy of neutron dose with a high dose of radiation and a lower dose of radiation at the bottom also was one of the elements that we consider for the Moon Village project. Even if we're using a different shielding strategy, we decided to have a super safe area at the bottom and leave the more exposed area with the activities and the function that actually were not requiring 24 hours, 7 days a week for the astronauts. And so this is the strategy that we applied. I don't know if I answered properly your question.
Okay, yes. Thank you very much.
So thank you all for these questions. Thank you, Valentina, for your really inspiring lecture. I was very happy to be here to listen your presentation of space architect, a woman, young. You are really inspiring for all of us.
Thank you.
And before giving the floor to Marco for the last remarks, I want just to spend a few words about the possible connection between space architecture, design, and interdisciplinary works. This is something we were discussing before this lecture started. Dava Newman has been recently, who is an MIT professor of aeronautics and astronautics, has been recently appointed the new director of the MIT Media Lab. So she will lead this design space in a way. So this will be very interesting moment, no, for joining. Even if the research will be multidisciplinary and interdisciplinary, whatever. But I think this is a very interesting way or in which research at MIT is moving forward, no? Bringing together different disciplines, and we will see what will going on. Okay, so thank you very much for your time, and Marco, please.
Thank you. So Valentina, I really want to thank you for this very fascinating seminar, and also for your research in sustaining human life in extreme environments. Apart from technical aspects, I would also like to point out that your work managed to combine beauty and utility very well. All the pictures, I really liked all the pictures. So I see also from the number of participants that the talk has been very appreciated, and I also really enjoyed it. Of course, you are welcome to visit Politecnico di Bari and Puglia in person as soon as the pandemic ends. So we will invite you as soon as possible. Thanks also to Analinda, and thanks to everyone for participating. Thanks again, Valentina.
Yes, thank you all, and I look forward to meeting you all in person soon. Thank you.
Thank you, and good luck for your career.
Thanks.
See you.
See you.
Bye.
Bye.